Hello everyone, welcome to today's class. Today we are going to look at indices as a topic, okay? So there are a lot of other topics that is related or that is associated with indices such as standard form and log grading, okay? So we are going to look at those ones after we must have finished discussing indices, okay? So when we say the word indices, what does that mean? It's the plural form of index, okay? And when we say the word index, what does that mean? We are familiar with using the word raised to power, okay, or power of. They are the same thing. So index can be uh, exponential, raised to power, power of, okay? So if I have a raised to power n, this can also be said that is a index of n, okay? So that's where we get the word indices from, okay? So that's the plural form of index. Now, we are going to explore when we put a number in a particular index. Let's say, for example, 2 raised to power 3. What does this mean? 2 raised to power 3 simply means that we have 2 times 2 times 2. So if I have a into, let's say, 5, that will give me a times a times a times a times a. Okay, so this is basically what the index or the indices mean. So now we have gotten the concept of indices. Now the next thing is there any laws guiding indices? Yes, there are laws guiding indices which we are going to explore now. Okay, so we are going to look at the laws, then we are going to see how we can apply these laws or even show how these laws are actually true. So under laws of indices, the first law we are going to look at is that, oh, meanwhile, before that, let us explain or let us label what all this means. Okay, we have already explained that when we have a raised to power n, it simply means that or it can be called a index of n. So this number here, okay, this a here is regarded as the base, while this n here is regarded as the index. Okay, so the number like this one here is the base. So this is the base, okay? And these ones are the what? The index, okay? Now, that being out of the way, we'll come back to laws of indices. Now, you need to be careful or you need to actually remember how this law look like, okay? You can notice that they have these two numbers that are multiplying each other has the same base, okay? This one is base A and this one is base A. So they have the same base. And if they have the same base and they are multiplying, you don't need to multiply. You need to do what? Just add the index. Okay? Just add the index. Now, how can we show that this is true? If you take 2 raised power 2 times 2 raised power 3, what does that mean? 2 raised power 2 will give you 2 times 2. Then this one times, then this one here will give you 2 times 2 times 2. So if you count all these all, you have 2 raised power 5. Because we now have 1, 2, 3, 4, 5. Okay, so another way you can also show that is that if you have, let's say, 2 raised power 2 times 2 raised power 1, that will give you 2 raised power 2 is 4 times 2 raised power 1 is 2, which is equal to 8, and 2 raised power 3 is the same thing with 8. Okay, so either of these two can be used to verify the first law of indices. Okay, so the next thing we do is to move to second law. So for the second law, we have that a raised to power n or a index of n divided by a index of m will give you a index of m minus m. Okay, now remember they have the same base. Please, if they don't have the same base, these laws cannot be applied. Okay, we cannot apply first law, we cannot apply second law. They must have to have the same base. Okay, so we can actually verify this. Remember, divide means over. So if you don't want to write an divided by am, you can as well write it as an all over am. Please, they are the same because you don't know the one that will be given to you in any exam that you are preparing. So if we use any of these, okay, any of these today are the same to look at, let's say, uh, 2 raised to power 5 divided by 2 raised to power 3. So 2 raised to power 5 is 2 times 2 times 2 times 2 times 2 all over 2 raised to power 3 is 2 times 2 times 2. So you can multiply everything here and multiply everything here and divide, or you can actually cancel out. Remember, because they are multiplication, we can actually cancel out. But if we have addition here, we can't do that. Okay, so we can actually divide like this. So what we have, 2 raised to power 2. So meaning that this will give us 2 raised to power 5 minus 3, which is the same thing with 2 raised to power 2. So these are a way of verifying that particular law of indices. Okay, so let's move to the next one. So the next one is that if we have a number here at our base raised to power 0, it will give us 1. Okay. Now we can use the third law to verify this. What do I mean by that? We can have 2 raised power 2 divided by 2 raised power 2. That will give us 2 times 2. Oh, this a raised power 2 divided by a raised power 2. We have a times a over a times a. And this will give us 1. That means a raised power 2 divided by a raised power 2, which will give you a2 minus 2 will give you 1. That will give you that a0 equal to 1. So you can see that it can be easily verified that that's what you're going to have, that any number raised to power 0 will give you uh, 1. So let's move to the fourth law. The fourth law, a raised to power 1 will give you a. So sometimes you just need to put the index, though it does not really change anything. So if I have 2, 2 is the same thing with 2 raised to power 1. If I have 5, 5 is the same thing with 5 raised to power 1. Okay, so we might decide to, of course, this is not index form of this number, but this is index form. So you can decide to write to an index form, which will give you 2 raised to power 1. Okay, so that's what we do there in case that you need to express a particular number in a particular index. Okay, now let's move to fifth law. So in this particular law, we actually call it fractional index. Okay. Now you will notice what happens there, that 1 over a n will give you a minus n. So I always tell students that this minus here simply means 1 over. Okay. So you have to have that in mind, that 1 over a raised to power n will give you a minus n. Now it can be just 1. For example, 1 over 2 can be written as 2 raised to power minus 1. Remember, this one here is not this. Okay, is because these 2 here can be expressed as 1. So that's why we have minus 1 here. Okay, just like this minus n. So we'll call it fractional index, and is a very important law in indices because we use it a lot of times. Okay. Okay, so here is the sixth law. You can see we have an index bracket, another index here. Okay, so what do? We multiply. So it's either you write it like this, nm, or n times what? n. Okay, so wherever you have something like this, so you can actually verify this very easily. For example, 2 raised to power 3 into 2. So this means, first of all, the bracket, that means 2 raised to power 3 times 2 raised to power 3. That's the meaning of 2 raised to power 3 into 2. Then 2 raised to power 3 will give you 2 times 2 times 2 times 2 raised to power 3 will give you 2 times 2 times 2. So altogether, 1, 2, 3, 4, 5, 6. So that will give us 2 raised to power 6, which is the same thing as 2 raised to power 3 times 2, or 2 times 3 whichever way you want to write that. Okay, so that's how to verify that particular law of indices. It's a very important law also, so you have to remember it, you have to practice it, and so that you can be able to apply it while solving a problem. So let's look at the seventh law. So this is the seventh law. Okay, we say that the nth root of a number is equal to the number raised to power 1 over n. Why this one is because a can also be expressed as 1. So that's the one you are seeing here. Okay, that's the one you are seeing here. So for this one, you can see that we have m here. So you now have m raised, or we can actually split this to make it look like this. How? We can have something like nth root of am as um nth root of a raised to power m, which will give you uh okay, which will give you am all raised to power 1 over n. And when you multiply, applying the last law that we looked at, we have a into m over n, because 1 times m will give you m. Okay, so you can play with it. You still get the same thing that we have there. So these are the laws of indices. Okay, so we have stated the 7 laws of indices. um, the next thing now is to look at the problem types. Okay, what I mean by problem type is the type of questions that you can be asked under these particular laws of indices. In indices, we can ask you questions that have just numbers. Okay, then we can have ask you questions that contains what? Algebra. So we can apply numbers to indices, we can apply algebra to indices. Now, when we ask you questions on numbers, what kind of question are we going to ask you, or what type of question are we going to ask you? The only thing we can ask you on questions on numbers is simplification. Okay, simplification. For example, you can be given a problem like this: 2 raised power minus 3 times 8 raised power minus 1 over 2 or over 4 raised power 2. You can ask to simplify this. Okay, so when you are asked to simplify this, is application of indices on just questions on numbers. Okay, so you can see it's just numbers. There's no unknown, there's no x, there's no y there. So we can also do simplification on algebra. So we still have here, let's call it number 1, simplification. Simplification, you can ask you to simplify uh, 2 raised to power 3x plus y times 4 raised to power 2x all over, let's say 32 raised to power x minus y. So you can see this one contains unknown. So we can ask you to simplify this. You can see that they look alike. The only difference there is that there are a lot of unknowns in this one. It can be uh, in one variable, it can be in 2 variables. Okay, this one is in 2 variables. So when it comes to question type, this is the only type of question we can have in indices. We'll just ask you to simplify. But in algebra, we can ask you to simplify, and we can also ask you to solve or evaluate. Okay, so solving or evaluating, we can ask you to do that. When we ask you to solve, it simply means that the question is going to, it can either lead to linear equation, simultaneous equation, or quadratic equation. Okay, so we are going to take them one after the other. Solve examples on simplification, the one that just involve only numbers. Then look at simplification, the one that involve unknown. Probably solve about 2 questions there. The one that involve both one variable and 2 variables. Okay, then we'll now look at when is it going to lead us to linear equation. We also need to look at when is it going to lead us to simultaneous equation. Then we now look at when is it going to lead us to quadratic equation. Okay, so you can see that is a very long journey. So I need you to fasten your seatbelt. Okay, so let's start with a problem of that nature. So this is our first example: 3 raised to power minus 1 times 27 raised to power 1 over 3 all over 9 raised to power 2. Now, whenever you are solving any problem on indices, the first thing that you need to do, or the first thing that you have to always remember to do, is to place every number to its lowest base. Even if it's not going to be in lowest base, let it be in the same base. For example, you can see 3, 27, and 9. We can express all these numbers in their lowest base. Okay, now, okay, let me do something here. Okay, so I'm going to write out the lowest base of most of the numbers. Okay, or I'm going to write the lowest base and write the numbers that have that particular number as a lowest base. Let's start from 2. Okay, of course, 2 can be expressed as 2 raised to power 1. So 2 is the lowest base of 2. Then we have 4 there. We have 8. We have 16. We have 32. We have 64. We have 128. We have 256. We have 512. We have 1000. 1020. I think so. No, 1024. Okay, so all these numbers you are seeing here, they have 2 as their lowest base. Then for 3, we have 3, of course. Then 9, 27, 81. 81 times 3, that will give us 243. Okay, I don't think they will give you beyond that. Okay, I'm just looking at the limit or the highest kind of number that you'll be given. So nobody will give you beyond. If it's going to be base 3, they're not going to move beyond 243. Now we can have 4 because 4 already has 2 as its lowest base. So the next one is 5. 5 will give you 5, of course, 25, 2, 125, and of course 625. So that's the maximum they can go for that. 6 will give you 6, 36. 36 times 6, that will give us 216. They won't go beyond that. 7 will give you 7, 14. Oh, no, not 14, please. 49. So that they can't go beyond that. 343. Then we can have 8 because 8 is already here. We can't have 9 because 9 is already here. 10, that will give us 10, 100, 1000. So 11, that will give us 11 and 121. They won't go beyond that. 12, 12 and 144. 13, 13 will give you 13 and 169. Then 14 will give us 14 and 196. 15 will give us 15 and 225. Okay, so these are the common numbers that we normally encounter during indices of numbers. Okay, so all these numbers have their base. Okay, so that anytime you see them, you have to know that, okay, this is the base I have to express this number to. Okay, all right, so I'm going to leave this here and finish up this so that you take your time a little to look at this while I'm solving that problem there. So the first I will do is to express each number here to its lowest base. 3 is 3 already have its lowest base as 3. Then times 27. So how many 3 will you get in 27? That's what we mean by the lowest base. So we have 3 times 3 times 3. You can count it from here. 1, 2, 3. So that will give us 3 raised to power 3. Oh, put that in bracket. Then you now have your 1 over 3. So you can see what I have done there. Then all over 9. 9 is 3 raised to power 2. So you can have that. Then have in bracket and put your what? 2. So you can see that I have expressed every number there in its lowest base. So the next thing I'm going to have is my 3, simplifying the bracket now. That's the next thing. So 3 minus 1 times, this one will give you 3 raised to power 1 all over 3 raised to power 4. So if you apply this particular law, that will give you 3 minus 1 plus 1 all over 3, 4. So that will give you 3 raised to power 0 over 3 raised to power 4. Okay. If you apply division here, you have 3 raised to power 0 minus 4, which is equals to 3 minus 4. Okay, so that's how to simplify that particular problem. So I'm going to clean everything and probably solve one or two other questions. Remember, sometimes, yes, sometimes they will give you a problem that will not have the same base. Okay, so all you need to do, put them in their lowest base. Okay, the ones that have the same base, take care of them, and the ones that don't have the same base, take care of them. Okay, so that's how to deal with a problem like that. Our next question is 125 raised to power 3 over 5 or over 5 raised to power 3 times 25 raised to power 3 over 2. So, like I said before, express every number in its lowest base, then you now simplify, applying laws of indices. So this will give you 3, this is 5 raised to power 3, that will give us 125 into 3 over 5 all over, down here, 5 raised to power 3 times 25 is the same thing with 5 raised to power 2 into 3 over 2. Okay, so that will give us 5 raised to power 9 over 5. That's what multiplying these two, all over, open this bracket first, 5 raised to power 3 times, when you open this, you are going to have 6 over 2, which will give you 5 raised to power 3. So that will give you 5, 9 over 5 all over, apply law of indices in these multiplication numbers here. You have what? 3 plus 3 will give you 6, so 5 raised to power 6. Then the next thing to do is to apply division law. So that will give you 5 raised to power 9 over 5 minus 6 over 1. Okay, so when you do that, 9 over 5 minus 6 over 1, that will give you 5 here, 9 minus 30. So that will give you 5. 9 minus 30 will give you minus 21 over 5. Okay, so that's the last answer. So you can check your textbook and look at numbers or problems on numbers in indices. Then um, apply it and solve some problems. And if there's any challenge, come to the comment section, or you can type the question, you can send us a message, you can send us message on WhatsApp, we'll attend to you. Okay.